projection effects of your camera, perspective distortion effects of your camera, then you have the lens blur, then you have your additive noise. And as I said, that additive noise still follows a Gaussian behavior, which means there's not much difference in what in the model before and model here. You can basically take the same value of variance over here, but keep in mind that it's a quantized version, so you have to take it from the camera pixel intensity. But the two important things that we model here is a perspective effect that has been encompassed in this alpha value. It takes care of this camera projection value of perspective through alpha p, which you can derive through camera image analysis. I'm not going to go into the math of it, but what it basically models is if you had some size of a pixel, how much does it translate to in your camera image at some distance and some angle between your transmitter and your receiver. Angle, both all three dimensions as well as distance. X, Y, Z.
So the camera projection is like some kind of a linear transformation, is it?
Yes.
So do you consider like using like a pilot sequence in order to, like in radio you'd be like, oh, I use a pilot sequence and I estimate the channel and maybe I build an equalizer, right? So is there an equivalent camera thing where you have kind of a pilot image and then you get to estimate what this transformation is and undo it, try to do a kind of an image equalization, if there is such a word?
Yeah, I think you can definitely send a pilot to estimate these perspective distortions. Here I'm talking more about how do you model this, try to understand how they, what's the math behind that. But if you were to estimate that at your camera receiver, either you could, like if I tell you what is the size of these pixels, there is some way if you, there is using the projection theory, you will be able to kind of reformulate that at your camera receiver and say, oh, it's probably going to be of you, the area is going to be that.
Roughly, as you showed that picture of the checkerboard, then you showed that it gets skewed,
yeah, it's skewed.
Kind of fit, and basically you untwist the image so that it looks straight.
Yeah.
Right. I think
it is a preamble.
So we need to. Okay. Yeah. I think.
So I guess there's two issues here. One is like in practice, like how do you build the receiver detector to exploit such thing? But there's a different thing, which is, well, what's the capacity of the system? And it sounds like maybe you're kind of focused on the latter rather than.
I would agree with that.
And exactly what you said is part of the computer vision.
Yeah, so it's coming to that point. Yeah. So go ahead.
So you're saying, oh, that's kind of in the vision part of.
Yeah, there is, as I said, there is a vision part to this, which I'm not talking a lot about it, but there is definitely a vision part. To give an idea of, as you said, you actually raised a good point. The first thing that you need to do at the front end is basically make this thing straight. That is, start aligning things. That's a very interesting vision problem that you've also been looking at. But what I'm talking about here is that if you have this alignment and you kind of estimated this either through pilot sequences or from this image itself over a series of images, how much information would you have transmitted, or how much information you have decoded successfully? What kind of techniques are best? I frankly don't know what is the best way. Whether you have to send a pilot, is it efficient, or can you just estimate it from the single image itself? That's some questions to answer. I hope that answers the question. And we have to account for the lens blur. So if you look at this formulation, what it's actually doing is basically scaling down the area. The blur is basically spreading your signal over multiple pixels, and you have to account for the effective area over which you can decode the pixel value. and this is the effective area reduction due to blur. If there is absolutely no blur, all that you have transmitted, the square pixel is going to be projected as a square, and the only perspective projection would, you would need to account for only the perspective projection. There is no loss due to blur. Effectively, it's the area scaling, as I said in the beginning. And we went ahead and we want, as much as we are analyzing this model, we also wanted to just validate it using a simple experiment setup where you would display these kind of white and black blocks of pixels on a screen and receive it using a camera. And this is a stationary setting, and you can see what you receive is this small region. That's where you have to decode the information from. Our interest is what is the signal to noise interference noise ratio on this region for each pixel on an average. What is the alpha value that you modeled, and alpha basically tells you what the effective reduction in the area of your pixel, right? And our camera tells me that spatial bandwidth, how many pixels of your camera are actually useful. And this is your spatial bandwidth, and the two-factor comes from respecting the 90% sampling theory. We're not doing anything fancy over here. We need at least 2 frames because you're doing a kind of on-off keying of BPSK system where either it's white or black, and you need at least 2 images to decode whether it's a white or black using a simple thresholding scheme. So let's keep the 2-factor over here. And signal to noise ratio is basically transmit power, interference, and noise. And you have the effect of alpha over here. And effect of alpha on the other pixels will account for your interference. Let's go ahead and plug this model into our capacity, use this model and use our experimentally measured values of these alpha and the signal to interference noise ratio for each of these pixels, the white and black pixels, and take an average value and plug it in. So the reason I talk about average value here is that it's pretty, it's actually for a convenience, but if you see it actually works pretty well. It fits the model pretty well, and I'm going to show you. The reason we're taking an average over here is that if you, ideally, the alpha for each channel between each pixel and your camera is going to be slightly different from each other. I mean, the alpha formulation that you get will be a function of your camera pixels too. But that's going to be that was a little cumbersome to actually compute for each of these camera pixels. You have millions of these pixels. So why not take an average of these values and see if that average value fits in. If not, we would have discarded, but we saw that it actually fits pretty well. The model fits pretty well with your analysis, and what you have here is basically your capacity in terms of camera, in terms of bits per camera pixel. Here, what I'm doing is I'm using number of camera pixels and number of screen pixels interchangeably. And since the number of camera pixels and number of screen pixels were same in this analysis, and the x-axis, you have your perspective distortion factor alpha in terms of percentage. 100% tells me that at some distance, you transmit your screen was actually imaged in your camera, and it occupied the entire image, entire screen image. And the resolution of the camera was set to about 2 megapixels, 3 megapixels. And let's take an example sample point. At this point where these transmitter and receiver was at about 2 meter distance, which actually translated to a point where you had a reduction in area over each dimension of 50%. So if alpha is 50 times 50, 0.5 times 0.5, so 25%. We can see that you can actually decode about 4 bits per camera pixel. Ideally, you should be able to decode 8 bits per camera pixel, but it's almost halved over there. It's exactly halved over there, and this translates to about 4 bits per camera pixels per frame, and times 30 frames per second camera, you're getting 120 bits per second, just for a single element. But when you start talking about the MIMO aspect of it, that is, you have 3 megapixels on your camera, and each could give you 4 bits. Each could give you 4 bits. You're going to get about 12 megabits just in one frame. again, keep in mind that you have to leverage the MIMO aspect. Keep in mind that you have to account for these interpixel interference. So all the receiver, I'm kind of taking for granted that all the receiver algorithms will help you to achieve this kind of capacity, but there's a huge effort needed to actually achieve this, and that's where you have to borrow a lot from computer vision theory, computer vision algorithms to achieve the same. But given that what are the bounds, that's what we have looked at it, and it looks like it's feasible, and looks pretty good. The data rate looks pretty good. But again, not only these kind of, there are more practical aspects that you need to consider. There's a heavy reality check that you need to do, especially for these kind of screen-to-camera communication systems. The first thing is there might be a mismatch between your size of your screen pixels, the transmit elements, as well as your camera pixel, which is the size on the image sensor array. Obviously, when you can say that you can neglect these are really negligible in terms of the order of a few micrometers, but these micrometers is what matters here in terms of interference. When you're building camera, when you're trying to build cameras and trying to build transmitter screen displays like these for communication purposes, these make a big deal. But when you start averaging these, that's where we kind of make it look negligible, and it kind of is negligible when you start averaging things. So there's a way out, but also you have to keep in mind that as a designer, you need to keep that in mind. The second thing is, this is a very, very important problem. There's a synchronization problem between a transmitter and receiver. This is, I think there are many people trying to address this issue, and there's no standalone solution that exists today, and we have also had a stab at it. The screen refresh rate, the screen is actually refreshing at about 120 hertz. You cannot see it, but if you were to take a proper camera, you would be able to see that it's actually refreshing over time. And the camera is also being sampled over time. Essentially, your transmitter and receiver have to be synchronized. It has to be a coherent system where they're synchronized. Then you can achieve all these kind of high data rates, and you can talk about capacity, you can talk about novel algorithms, which means you have to start building synchronization techniques for that. Maybe you can average over multiple frames, or you can use information over multiple frames, multiple images to synchronize, but that's just one possible approach that I think is possible. And thirdly, motion blur. As I said, the blur factor actually accounted for effect of lens in that model. I showed you that our experimental validation was for a stationary system. But if you were to move your camera around, you're going to get the similar blur effects, but due to motion. The pixels are going to start interfering with each other. The averaging over alpha kind of takes care of very slight motion, that is the hand vibration. If you were to just take your camera and point it at some screen, you have slight hand vibrations. So these are minuscule, and over averaging you kind of can get over it, not 100%, but close to 90% of it. But if you had really high motion, like a lot of, if you are actually swaying away the camera, it kind of looks like this. And if you just had, it kind of looks like these two, and it's only that I moved the camera pretty fast. I just moved it this way. And there's absolutely nothing you can decode from this just with your eye. And if you're just processing each of them using a simple thresholding, nothing's going to happen. But thanks to image analysis, image processing community, they have developed some techniques called deblurring. It's basically a kind of equalization where you invert the blurring function and try to retrieve back an original signal. You can, of course, it's not as close to the same, but it's much better than this. And definitely you can see that this is much, much better than this. Not only that, you also, as an optical channel, as a visual channel, you always have this problem of occlusion, where a part of your signal is going to be seen, which means you have to start adapting for these kind of changes in your system. But overall, what we are looking at in the far future is that your mobile phone cameras should be able to communicate with the pervasive LCD screens and light emitters that exist everywhere. You just go to Times Square and point your camera to a Times Square screen and just buy a ticket for a theater show. And over this first part of my talk, we've talked about a channel model for visual MIMO, which accounts for these unique perspective distortions. Talked about how distance and angle play a key role in the capacity of visual channel. And then we took a use case example of screen to camera communication and try to validate, analyze the capacity and validate it through experiments. And we saw that, of course, same problems exist, but we looked at it in a more practical aspect, or you just could see it in front of you, what those perspective distortions mean, what the blurring mean, and how much it is actually reducing your capacity. And in the end, as I keep telling, and I'm going to keep telling over this talk, that whatever things you build have to go hand in hand with the computer vision algorithms. Though I'm not going to concentrate much on the algorithms, but they have to go hand in hand. And one thing, this was just an example. So we went ahead looking at this. We kind of got kicked up by the idea of using visual MIMO for different kinds of applications, and we tried to prototype this for something, for a vehicular-to-vehicular communication. Of course, this picture just shows the feasibility of using visual MIMO communication. We have LEDs communicating to a camera. And the two important things of this prototype is that it's very low data rate system, because what we're doing with the LEDs are being modulated using on-off keying, just switching on and off at 100 hertz, and hence your data rate is 100 hertz from each LED, and you have 8 LEDs over there, so you're getting about 800 bits per second, much less than 1 kilohertz, 1 kilobits per second. And secondly, there is some adaptation we are allowing for mobility here, that is using computer vision tracking. If you were to move this camera, it looks like a more static setting, but if you were to move it more in a controlled fashion, the receiver is able to track this poster and hence the LEDs. Use a simple template-based matching. You can use more sophisticated algorithm like feature matching to track this transmitter, basically identify it and then decode the information. But is that enough? It probably shows you the feasibility of this approach, but is that enough to actually adapt to every possible impediments in your visual channel? Can we also adapt to improve the throughput of communication over here? And again, let me motivate you with this vehicle-to-vehicle application. In reality, how you would see this visual MIMO applied in cars is that you could think of someone pressing you're pressing a brake pedal, and these brake pedals being integrated with your car brake lights, and they could send some telematics data, they could send some sensory information, or just a warning sign to a car behind which decodes that. But the problems are that the channel is heavily mobile, and which means you can get occluded. You need line of sight, you need the car brake lights within the sight of the camera. If you even miss one brake light, can you do something to just receive information from the other? Can you adapt in that way? Is there any way you can also account for the perspective distortion, the distortions that occur in your visual channel when the car is far away, or when it's closer, or it's at an angle between you? Can you also adapt to that, these kind of perspectives? And that kind of leads into the second part of my talk, where I'm going to talk about how you adapt to these kind of perspective effects in your visual channel using MIMO data adaptation. To recall this picture where you're transmitting using multiple light elements to communicate to camera receiver, where these, for an orthogonal channel, everything gets properly imaged onto different pixels, very non-interfering pixels. And assume if you have a feedback channel, the receiver telling the transmitter that, hey, I did not receive LED 1, I did not receive information at all, you are uploaded. These kind of some simple acknowledgement-based information or any feedback information would be really helpful for the transmitter to adapt itself to communicate in a way that you can actually either improve the throughput or keep the link more stable in a mobile channel, such as vehicular. And again, it recalls that you can use orthogonal channel to multiplex information, scaling your data rate, or you could send the same information over that channel. Send the same signal over these LEDs, or all the LEDs, and get a signal to noise ratio gain, and hence improve your capacity in a different fashion using diversity. So with this motivation, I'm going to talk about rate adaptation in visual MIMO, and the key challenges that I'm addressing here is perspective distortion, the lens blurring, and the occlusions, which you cannot ignore in a visual channel. As I said, in this we looked at the rate adaptation problem in a more transmitter rate adaptation scheme, and we defined something called modes. Modes are basically different transmission configurations of these light emitters. What is the geometrical configurations of these light emitters that you would choose to send information, or which helps you adapt over perspective. That is, if you are at a large distance, you know that you're at a large distance, you would actually send all the information over, send the same bits over all LEDs and use some diversity schema to receive, and hence keep the link active. At a shorter range, you could actually multiplex information over different LEDs and have a neat orthogonal channel. So the visual MIMO rate adaptation functions this way. The problem is to basically efficiently choose a transmission mode such that you can maximize your data throughput. That's the goal. And the constraints are your distortions and resolvability issues due to blur and visibility issues. Okay, and this gives you the schematic gives you a better understanding of what the model or the system looks like, or the adaptation system looks like. The transmitter is basically sending packets. We look at a packet-based communication system with some appended CRC over each packet for error control. The receiver decodes these packets and tells you whether there is an error in a packet through an acknowledgement. And we use a packet error rate metric as a reliability metric, and based on this packet error rate metric, the transmitter adapts its mode, and then receiver processes that and keeps going on. In simple words, basically what I'm trying to say is that the receiver tries to find out which of these LEDs are occluded, and then if whatever LEDs are not occluded, for those occluded you cannot do much, right? But for those that are not occluded within the view, what is the best transmission mode you can set? Sorry, it's a transmitter actually taking these decisions. What is the best transmitter mode that you can set to achieve data throughput, improve your throughput, or maintain your link? And so we proposed 3 schemes of it, and I'm going to go over these schemes one by one. The first approach is basically exhaustively search for errors over each LED. What happens is something like this. Each LED in a sequential fashion keeps transmitting a packet, and the receiver waits for until all the packets are being transmitted and sees which of these LEDs are in error. Then it creates a mapping and tells the transmitter that, hey, these are the LEDs that are in error. You kind of need to adapt your mode in some way. But this is a very, very inefficient scheme. As you see, it really takes a while to actually exhaustively search all the LEDs. And if you were looking at extremely large arrays of LEDs, this is going to be an extremely inefficient approach in terms of time as well as complexity. The next approach is you can leverage from the spatial dimension. Actually, you can start sending some repetitive patterns over space. You can start sending some repetitive patterns, basically it's a repetition coding over different LEDs. You can repeat the patterns. A and D could repeat the patterns, but one possible way is the regions A and D can have bits that are complement of each other, in which way the receiver and similar B and C would do the same. Then you can have some kind of protocol that tells you which of these regions are exactly occluded and what kind of mode that you have to set. Definitely, it's much faster than exhaustively searching. It's nicely using the spatial diversity over here, but the trade-off is that you have to start thinking about these kind of smart spatial patterns for different LED configurations. And let's take an example of a car. Different cars have different configurations of their brake lights. And are you going to build different kinds of smart spatial patterns for each? Is there one smart spatial pattern? Or those are the kind of questions. But definitely this is an approach that you can. The spatial dimension is something we definitely leverage. Thirdly, which is it's a more efficient scheme, would be to transmit all the packets in parallel, assuming that you have this orthogonal channel. Even if you don't have, then just send the same packets over all the LEDs and try to decode it to the receiver at the same time. In this way, at one go, you're able to tell which of these regions are in error, which of these LEDs are in error if you had a completely orthogonal channel to each of these LEDs. You really don't need a training sequence. You don't need to invest more time and power on that. So this definitely looks like a more, it's definitely a feasible approach. It's also definitely a faster approach that was hypothesized that. So we went ahead and did a stress test for this using a simulation, used some traces for this, a real road traces where we were following a car with brake. You may not be able to see in this picture, but these are actually glowing. It had an array of 9 LED, 3x3 LED configuration, but it was in a trapezoid again. So it's these kind of configurations change in different cars and different vehicles. And as you go further away, these become more invisible even to the camera. Then you have to start thinking about a different mode. So the question is, can you start adapting? Will your algorithm adapt to this kind of distances and different occlusions that can occur in a real vehicular channel? So that, again, the idea of adaptation is to change your mode when it's required, which is when the distance changes and when it's occluded. And we use the throughput as a metric over here. We use average throughput, which is averaged over a time window. B has to be 1 second over here. Basically, the averaging was over one. The adaptation window was over 1 second, and we are averaging over 10 seconds of 60 frames per second camera window. And the rate is, we borrow from the channel capacity values. Rate is basically, we plug in the channel capacity values that we have analyzed earlier, and we find what is the number of packet, just plug in the packet error rate values into these and find what is the average throughput for each of these adaptation schemes. For the distance case, we see that definitely one unanimous thing is that the index-based approach performs well. Index-based approach performs the best of all. As I said, it's definitely an efficient approach to transmit everything at a go and try to find it out. Try to find out what things are in error and adapt immediately to it. You don't waste time on training sequences. You don't waste time. You don't waste your bandwidth on exhaustively searching for these. It's also interesting that the index-based approach is very close to an ideal case where what if the transmitter already knew exactly what are the configurations that it has to, or exactly what configurations and modes that it has to be setting at different points of time. Clearly, this shows the feasibility of adaptation in visual MIMO channels, and we have taken steps towards that. And you can see that the kind of adaptation that you do in visual channels is a little different from how you think in radio channels, where the adaptation has to be really fast over time. The radio signal is changing so fast, the multipath components are arriving at your receiver so fast, which means the link quality can change really fast. So the thing is, you can really do it relatively very slow over here. And challenges that you're addressing here are different. It's around multipath, it's around interference from multiple, contention from different antennas. In one way, it is actually contention from different antennas, but in a more perspective fashion. The perspective always plays a key role in this. So to summarize what I've talked in the second part of my thesis is that basically it talked about the potential of using, adapting your throughput, adapting your performance of visual MIMO system to these kind of perspective channel distortions, like blur, visibility, and occlusions, which should be very common in any kind of visual channel. And we proposed we pose 3 approaches, each increasing in the order of complexity as well as increasing in the order of efficiency and performance. And then we use the vehicle-to-vehicle communication as a key driving factor for this, but it's not really there. This was just an example use case, but you can also think of this kind of adaptation happening in the screen camera communication, where you can keep changing these block sizes over time. What if the camera tells the screen, or the screen knows what are the different configurations of this white and black blocks that it has to select to efficiently, so that the camera can efficiently decode all those blocks and achieve a high throughput, as we have theorized over there. It also, if you didn't have a back channel or feedback channel, you can also think of the transmitter adapting as well. The transmitter having some kind of coding in it, such that it prioritizes the information over different levels of these spatial configurations. Something about it leads to something about hierarchical coding. You have these configurations mapping to different hierarchies of information and the receiver decoding. This is all something that this kind of work would lead to it. So far I've talked about channel modeling, I've talked about in visual MIMO, which is a very perspective dependent communication channel. And I also talked about how do you adapt to these kind of perspectives in this channel, and driven with some kind of applications for vehicle-to-vehicle and screen-to-camera communication. But in the next part, we'd like to ask this question. Okay, we are trying to address this perspective, model this, but is there any way we can find the perspective using this? What lessons have we learned? What are the things that we know about this optical channel and this visual channel, that you can start finding the perspective, which is, can you find the distance, can you find angle using these approaches? And that leads into my third part of my talk, which is localization and visual MIMO. So I can confidently say that the cameras today have become more mobile. Like, you have a camera at your fingertip almost all the time. You have it on your vehicles. You're also interested in wearing them. So things are moving around, and the sense of finding perspective, of finding where you are, where things are, where the receiver is with respect to space, is kind of getting very interesting. It will be very useful to know, and that's precisely the problem. Where things are in space, where you are in space, that is also interesting. Basically, the problem is symmetric over there. And what is the thing that is in front of you? What is the thing you're looking at? What is the thing that's actually in front of the camera, right? So you kind of need some identity. You kind of need some spatial perspective that you need to decode, that you need to find, which is distance or angle or position, as a matter of fact. This is the problem, and answering these kind of questions is something the research community is already at, and it's not stopping there. People are leading it to applications of augmented reality, where you want to more and more interact with the physical world, and the physical world actually also wants to interact more with you. There have been designs already there, and we're very familiar with these today. And there are some approaches in the research community to how would you actually find your perspective, how would you find where things are, using something called passive markers. One common thing with both these approaches that I show here is that you use a camera as a receiver, right? You can use a camera as a detecting device that detects these kind of markers and tells where these are. Then augmented reality is just another application space to these. Then you have this the system from ByteLight, where they are actually sending positional reference from using these lights, these lamps, fitting some custom transmitters over that is sending the positional reference to your cameras that you hold, and that's going to help you navigate you in this room and in this building and so forth. Position is the key. But one thing with the camera is that it's a highly energy intensive device. You think of it, in all reality you would want, if I tell you that I can position you all the time, I can navigate you all the time, you would want the receiver to be on all the time. Okay, I just need it now, and do I need to switch on my receiver at this point of time? Is there not a system that keeps telling me, gives me some feedback of my perspective all the time? And if you were to keep your camera on all the time, there is no way you're going to operate it for a few hours. Right? Doing other stuff, just the camera on, is going to just die in a few hours, and you can't even think of a real-time system that just uses the camera and keeps it on always on mode. But cameras are real. The idea of using the visual channel is very, very interesting. So we took we took a stab at this and figured, okay, let's step back and try to understand. A visual channel is basically an optical channel. The key driving, the main advantages of this, and the main characteristic of an optical channel is the high directionality. So there's already a sense of perspective in an optical channel. Can you not leverage that to find where things are? Can you not find angle? Can you not find distance between things in space using optical? Let's go ahead with that. But communicating ID information, what things are, is pretty energy intensive again using optical. So just modulating a light beam is going to cost you much, much more than just sending few bits over radio. And that's where we leverage the radio, which has been, we have known this for a while, that you can communicate lots of bits with extremely low power. And today we have these battery powered devices, RFIDs, that can send you few bytes in just using a console, and these can last for years and years. So let's leverage the advantages from both of these. Let's use the best of these both worlds and get a best hybrid system out of the two. That's what we did. So we built a positioning system that where you have a transmitter that which we call as radio optical beacon transmitter, that or a tag, that as we call it, contains a radio chip. It's an RFID chip, as well as optical element, an optical LED, an LED transmitter with its supporting circuitry. What this does is basically the radio is the optical LED is just sending a light beacon. It's just beacon, it's not communicating, and at the same time the radio is actually sending a few packets, bits, and what it encodes in the packet is basically your ID, and we would use this radio channel as a back channel, as a control channel for these. It's synchronizing the optical strobe as well as your optical strobe with your radio signal. And leveraging that at your receiver, you would use the optical strobe to sample your signals over an array receiver, array of photodiodes, spaced at some geometrical fashion, which will help you estimate angle and distance. And you have some circuitry around, and you have an RFID, a similar chip like this, which functions as a receiver to decode your ID as well as control the radio channel. So you have basically an optical channel and a radio channel functioning together and both synchronized. How does this help? By synchronizing your optical channel with your radio channel, the receiver will exactly know when to expect that optical signal. So I know that, oh yeah, I'm going to send you that optical strobe right now after this radio packet within a few milliseconds. So the receiver is waiting for it, which means the transmitter can send an extremely high intensity radio strobe, and since it's extremely high intensity, you can actually send it for an extremely short duration. That is, we are operating in the order of a few microseconds. You can send it for a very short duration, and which means that the total energy, light intensity that you're sending is pretty high. But since you're just sending for a short duration, and then the transmitter can switch off, you'll conserve a lot of energy, and I'm sure what are the energy gains that we get in this. So just to refresh what I talked about, the mechanism in this approach is basically you would send a radio signal and followed by an optical strobe. And in this specific example, in this specific prototype that we built, we use infrared as the optical channel. Infrared is good because it's very unobtrusive, so you don't really see the light blinking all the time, and it's not going to hurt your eye. So basically, it's invisible to your eye. So that gives a very neat aspect of it. So you would send an optical strobe immediately after your radio signal, and the receiver samples the optical signal, then samples some noise after that, because it knows what is the size of what is the duration of the optical strobe, what is the duration of the radio packet. And by doing this, making sure that each transmitter can keep doing this periodically and send the radio signal, then the optical strobe, and sleep for a while. And if you keep the sleeping duration sufficiently large enough and differentiating between transmitters and duty cycling them, you will be able to achieve the energy gains, as well as making sure you kind of have a multiple access channel. Multiple tags are actually communicating with your receiver. You can find where tag 1 is, tag 2 is too at the same time. So high intensity strobe, extremely short duration, synchronized RF channel, and ID using RF channel. We have kind of built a positioning system using this approach. So again, what happens at the receiver, because I'm talking about cameras, and the only difference is that the similarity is that it's an array receiver, but it's not a camera per se. I would call it as a 3-pixel camera in quotes, because you use 3 photodiodes. What it's doing is it's basically sampling the signal over the optical signal over it, and the optical signal intensity is a function of your distance, angle, and angle in 2 dimensions. So you have 3 equations, 3 unknowns, and you can nicely solve this out. So we went ahead and prototyped the transmitter, we prototyped the receiver. These are some specifications for your radio. The optical strobe is at 10 microseconds. Of course, this is configurable. And when I say configurable, it changes your performance. If a 10 microsecond strobe can help you achieve a range of 3 meters, but as I will show, if you increase it to 500 microseconds, you get about 10 meters. And with this prototype, we will achieve plus or minus 20 degrees or 40 degree field of view. Yeah, this is the first version of our prototype, and we went ahead and did a stress test for this again. We wanted to apply this to a very practical scenario where you would use these kind of tags fitted onto objects, and the receiver, since it was really small, we fitted it onto a glass, as I showed you in the picture before. We fitted it onto a spectacles, and to basically illustrate that this can be used as a wearable system and something close to augmented reality glasses. So if the experimenter was wearing the glasses with the receiver on, and the tags were placed on different objects in different scenarios. Everything is in WinLab. All these should look familiar to you. Posters, then each shelf of your bookshelf, and a small alley, then different objects in your in a conference room, and a very cluttered space. This is my desk space. Nothing better than a grad student's desk space for a cluttered space, and different objects in cluttered space. This kind of encompasses a pretty realistic scenarios where we use this, and of course it's limited to indoors because we're using infrared. So these are experiment scenarios, and one thing, the key important fact, one important thing was, since you're wearing it, you really need to know what the ground truth is if you want to compare. You want to know how well the system performed. So we just made a small contraption of the glasses fitted with camera and an infrared allowing filter, which is blocking visible light, and the image will basically look like this. And getting your angle and distance from this is pretty straightforward. Angle from this is pretty straightforward, knowing the XY coordinates. So we were interested in 2 important metrics. One is recognition accuracy, how well you can estimate the position in terms of angle, distance. We kind of take it for granted here that, and it is reasonable, that the IDs are being received correctly, because for this scenario we just had 5 tags and being duty cycled at 1 second interval, which means there was almost no contention at the rate at which we were duty cycling. So IDs were fine. We're getting all the IDs. We want to see how well the positioning is. and of course the energy gains. So if you look at the horizontal angle, that is the azimuthal angle, this is all with respect to your reference and basically the center of the spectacles. What is the horizontal angle error and what is the vertical angle error, which is basically the vertical space for different scenarios, poster, bookshelf, office room, and cubicle. One thing is that the median accuracy was within 1.5 degrees, which is very good. We're pretty happy with that. It kind of tells you a very pinpointing accuracy. 1.5 degrees translates to a few centimeters of distance, a few centimeters in position from the distance, from the range that we have achieved. And they're pretty consistent over these kind of scenarios, which is promising. Again, when we looked at the distance estimation error, we were within 40 centimeters of accuracy. I really feel that we can improve this. So as a very core, accrued stress test, but I'm sure a lot of things can be done to improve the distance estimation, much to very fine grain of less than few centimeters. The next thing was we want to really see what's the battery lifetime for this. What are the energy consumption levels? The way we measure the energy is we plug these prototype tags into an oscilloscope, and we wanted to see what is the battery drain. What is the battery drain for each of these states of your radio optical tag? Again, let me remind you, this is the energy consumption of your transmitter. We're interested in reducing the energy consumption of your transmitter, because you would see these kind of tags fitted onto these objects. And you can have a receiver which it is possible to recharge that over time. We were not really interested in looking at the energy consumption of your receiver or optimizing it to a level where we achieve the transmitter. But transmitter is very important. You can see that there are lots of tags around these early radio IDs. But this is kind of deployment that you're going to look at, and you just cannot keep replacing them at every yard. It's not possible. So what you see here is that at the radio idle mode, which is when it starts when it's switched off and it starts it's getting ready to transmit, and any delay in between, and accounting for all the small gaps in time over which it's idling out. This is the energy consumption. Then there's the radio transmit where we transmit a 13-byte packet, and the infrared transmit where you send the strobe, and this is for a 10 microsecond strobe, and then you have the sleep time where the consumption is going to really be small. The one takeaway is that it's on the order of few millijoules, and the average power, if you see, is milliwatts. Microjoules, and the order of microwatts. That's the key here. I have not put the numbers exactly over here for a camera, but if you were to just operate the camera, just for taking one image, the average power consumption is about 200 milliwatts. So I would say in the order of milliwatts, we're getting at least 2 orders of magnitude gains in this. And this can translate a few years on normal batteries that you can use. So again, let me remind you that you definitely have this trade-off in terms of the performance, the range that you can get versus the average energy consumption, power consumption of this system. If you were to use a very short strobe of 10 microseconds, you will get 3 meters, but a bigger strobe, but still in the order of a few microseconds. 500 microseconds, you're going to get about 10 meters, which is pretty good for actually indoor positioning. In this room, I can find where things are pretty accurate. That's what it means. So going it further, I showed you the first prototype was 20 plus or minus 20 degrees, which is 40 degrees of field of view. We prototyped the second version where we were able to achieve 150 degrees of field of view, and that's where we're heading to. We kind of trying to build an omni-directional transmitter so that you can get 360 degrees of view. This is kind of things that you can get to. But of course, keep in mind that the energy consumption is going to be quadrupled a year, with just 4 parallel channels at different angles. And there are a lot of things that you can think in terms of the protocol design. Can the transmitter or the receiver opportunistically communicate with each other? Or can the receiver be switched on only when the transmitter is within view? Or the transmitter tries to know if the receiver is in this room. Like if all the transmitters are here and I'm wearing the receiver and these kind of always sleeping, and only when I come into this room we start positioning ourselves. In which case you can really scale up your battery lifetimes. So overall, in this third part of my thesis talk, I was talking about novel designs in localization and positioning in visual MIMO using the idea of array receivers to find your perspective in space. And we were very much interested in optimizing the energy consumption of these kind of devices for this particular application, and built a new scheme where you can synchronize using a radio control channel. And definitely this can be taken up in many other venues. We prototyped this, we achieved about 1.5 degrees of accuracy, actually up to a range of 9 to 10 meters. And we saw that the battery lifetimes can be really large, very much practical for a real deployment. And as I said, it doesn't stop there. Positioning is just enabling the technology, but what you would see as reality, as augmented reality systems, you can think of localization systems, energy optimization with these kind of designs. So overall, with all these three parts, I hope I really got you excited about camera-based communications. How do you use cameras for communication? I introduced you a channel model, a communication system design model, went through some use cases and went through some applications of vehicular and mobile computing where you could transmit from screens and receive with your mobile cameras, and talked about localization, and positioning, which is a pretty hot topic today. What I want you to take away from this thesis is that camera communications is great. It's very interesting. It's very interesting, and it's very exciting. It's going to be there, but there are many things that you need to keep in mind. Perspective distortion is something you have to live with. You have to address these in whatever way. You need to work around these camera limitations. Definitely, a 30 frames per second camera on your mobile phone is not really going to change much over the years. It does not, and we hope that it definitely changes. iPhone had this slow-mo cameras, which can slow-mo feature in their cameras with 5S. It had 120 frames per second, but that's not enough. I'm talking about millions of frames per second. Maybe far into the future, you'll really see cameras in your hand which can do these kind of sampling rates. And power, any communication system design. Any system design, you need to keep in mind that power is a key factor. You have to optimize for low power and high mobility tolerance. We're talking about mobile wireless communication today. And as I keep stressing on it, the visual MIMO idea actually brought a very nice, it was a synergy between communications and computer vision techniques. These have to go hand in hand. And I'm really happy that our team was one, took that perspective of building in techniques from communication, techniques from computer vision, and trying to build that. Today I gave a very communication system design perspective, but there's much more to it. And with that, I really want to thank all of you for coming here, and at this point I'm really short of words. So I have to thank Ray, Ivan, and for really believing in this project and visual MIMO. I can still recall the days when we, Marco and our team were writing the proposal, and we never knew this was going to take up, and eventually it has shaped up into my thesis. So I'm really happy the way it shaped up. WinLab actually believed in it. And I have to thank Tom for just immediately agreeing to be in my committee when I just pinged him, and showed some lot of interest. I know he's also working in this area, but not exactly camera communications. So it's good to know someone is interested in your work. And of course, all the faculty over here whom I've interacted with, have TA'd with, it was a great experience. Those 2 years I just cannot forget. And I've interacted with all the faculty over here who have given a lot of comments, a lot of appreciation for the kind of work we did. And especially Rich, thing is, whenever I sit and talk to him, he kind of motivates me and increases my curiosity by 3 dB every time. Last but not the least, my advisors over here, Tristan, Narayan and Marco, you guys were great. The best thing about this, I can go pages over talking about them, but over time, what I saw in this team is that, including Vengia, what I saw in this team is that there was always a passion to get things done in every possible meeting, and we met almost every week over the past 5 years, and there's always this passion to getting things done, and you guys were like literally kids, and you were so interested in the things that we were doing, and that kind of appreciation and motivation keeps you really fresh as a PhD student, and I learned a lot from you guys. And as I said, I actually grew up with this team, and wherever I am today and whatever opportunities I'm getting, it's a big dedication to you. And of course, I have to thank all my friends, and I'm not going to name people because if I forget anyone, some people are going to thump me on my head. So I'm not going to name, but you know, the best part was I was able to interact with all of you, literally all of you, and I was also able to advise / mentor so many students around within this in this whole course. High school students, undergrads, grad students, and each and every one taught me so many things, and I just can't thank you enough for that. And it's a great thing. And I still thank all my friends over here who have helped me, and outside people who are waiting for my call to know what the result is, and my family back home. With all this, thank you, and to end up my talk and open for questions.